Hi everyone, and welcome to our very first session of our dynamics class. So in this video today, we're going to be starting our very beginning into our journey of what dynamics is and what that looks like. And the first thing we're going to start with is going to kind of feel like review. Really, this dynamics class is building off of everything that you've learned in statics and physics so far. So in statics, when we were looking at systems of, let's say a particle or some rigid body, when we were looking at these forces acting on a particle or rigid body, everything always equaled zero, right? So in statics, we had this idea always that whatever the summation of the forces is on that object is going to equal zero. It's not accelerating. It might be moving at constant velocity, but it's not accelerating. All of the forces are going to sum to zero. And the way we're going to take that a step farther in dynamics is now the big concept in dynamics, the big thing that makes it different from statics, is that all of those forces that are on that object now do not equal zero. We're no longer working in equilibrium. Instead, we have some kind of acceleration. Right, so some of our forces is going to be mass times acceleration. That's Newton's second law, and that's really going to be the basis for this class. And these are a little bit different than if you do like a strength of materials course, where again things may be in equilibrium, but there the bodies aren't rigid. There we're dealing with the deformation of bodies, how those things move and fail. So in this class, it's really just how do we take those forces? How are those interacting? What does that look like? And the big portion that makes up dynamics are kind of twofold. The things that we talk a lot about in dynamics are going to be the kinematics of things. Whoops, that's not how you spell that. That's an N. Kinematics. And kinetics. And these are kind of the two major overarching umbrellas of the way that we talk about forces in dynamics. So kinematics is more of like the geometry of what's going on. And this is what we've previewed a lot in your physics classes before, right? The kinematic equations, using position, velocity, work and energy, impulse and momentum, all these things. But kinematics more so deals with the geometry of what's going on, whereas kinetics deals with the forces. Kinetics deals with those free body diagrams, and dynamics really brings both of these things together so that we can analyze problems in a more scientific way, right? Just like we learned algebra so that we could learn Calc 1 and do more complex problem solving. We've learned statics, we've learned physics, we've learned calculus. A lot of calculus is going to show up in this class. All of those are combining together to give us dynamics, which will then be another baseline for if you move on to higher level engineering classes, especially in, maybe aerospace or mechanical, fluids, all those kinds of majors. As you get deeper into your engineering school, deeper into those topics, this will really become a base layer of knowledge for you. So today we're going to start with kinematics, right? And it's going to feel a lot like physics. It's going to feel a lot like physics review, but it's still really important that we nail down this kinematics so that we can use it when we build into the kinetics with work, momentum, impulse, all of those kinds of things. So the first topic we'll get into is rectilinear kinematics. And all this means is that we're looking at like the most simplest kind of kinematics we can look at. This rectilinear means just kinematics in a straight line. Right, so straight line kinematics is what we're looking at. Not even adding another axis, just straight line, rectilinear, straight line kinematics to start us out and really get our terminology down and understand what we're talking about in kinematics when we're talking about kinematics so that we can go on and solve more complicated problems. So when we're talking about kinematics and the geometry of things and how they're related to each other, we're really setting up problems that relate position, velocity, acceleration with each other and with time. So let's kind of talk about all this terminology, let's write out each of these things just so we're all on the same page and kind of familiar with these terms. So when we're talking about position, it would help if I could remember how to spell position. Position we often see denoted by the letter S. The letter S. And position just tells us where something is in space. So if I have, again, we're looking at a straight line for this example. I have some kind of straight line. This is maybe my origin right down here. And I've got a particle on that line. We're going to be doing rectilinear kinematics of just a particle. I have a particle on this line. My position is just that distance s from some origin, right? So position is just the distance from my origin. Whereas I could also have displacement, and displacement may be different from our position. So displacement is really a representation of a change in position, right? So I could have initially been located at this point S, but then maybe my particle moved, right? And he has a new position, where now he has been displaced from this original position to a new position of S prime, we'll call it. So this is the change in position. Change in position is our displacement. Delta S, representing the change in position. For this new position distance, you can call it S prime, or sometimes you may see it as the new distance is S, and that original distance is S naught, or initial. So S minus S naught. New position minus initial position. That's going to be our displacement. And this again can be different from the distance traveled. The total distance traveled that the particle has gone could be different from the position and from the displacement. So distance traveled, usually we see that denoted with an S sub t, to note that it's like a total distance, total area covered, total length covered. Because, for example, our particle could have started here, it could have moved back, gone way back past the origin, and then maybe it moved up to S prime. So this distance traveled covers all of this that it's gone over, whereas the displacement does not. Right? ST would cover everything, everywhere that particle has been in that same time, even though it may not match up with what the position is and may not match up with the distances. Right? All of these have directions. In this case, our position is a vector. Right? All of these terms, our position, velocity, and acceleration, are all vectors. It matters what direction they're going in. Whereas distance traveled is really a scalar. It's just a summing of the total scalar distances traveled, not including signs for position, signs for direction. So these are kind of our basics for position. We also can get from position to velocity, right? There is a relationship between our position and our velocity. And this you may have seen in calc before, you may have seen in physics before, that the way that we can get velocity, v, also a vector, we see this denoted with just a lowercase v usually, is the derivative of our position with respect to time. Right, and again, that's our vector. Velocity is a vector. It has direction to it. It is our, it's our speed. Where speed is just the scalar form of velocity. So velocity has direction, tells us a movement in position over time. So the derivative of position with respect to time gives us our velocity. And likewise, we could integrate our velocity with respect to time in order to get our position. So we can move between them. right? We have this relationship between velocity, position, and time. We can move between those. And this, of course, gives us our velocity at one instant in time. So we can calculate it instantaneous velocity. This is what our derivatives and our integrals calculate for us. But we can also calculate an average velocity. If we want to know what the velocity was over a certain amount of time, not just instantaneously wherever we're taking a snapshot in space, we might say, you know, what was the velocity over the duration of 5 seconds? So our average velocity is going to be our displacement over the total amount of time. So whatever that change in position is over the total amount of time that we're interested in, that's going to give us an average velocity, which again is different from average speed, right? Since speed is a scalar, it does not matter what direction we went in. Since speed is a scalar, it's going to include it even if we moved forward and then move backward and then move forward, which could have a different average velocity than if I just moved, move forward, backward, forward. Those signs matter in the average velocity, whereas they don't in the average speed, the scalar average speed. So that little bit of differentiation there between average speed and average velocity, average speed, which we often see still denoted with a V, but is a scalar. So average speed, you might see a V average with like an SP on it. I usually just write VSP. You can write it either way. Move that. So our average speed is going to be the total distance traveled over that change in time. So again, just nuanced differences between whether we're talking about an instantaneous velocity. So this is instantaneous, a snapshot in time, one moment. Instantaneous velocity, average velocity, or average speed. All of those could be different values for the same amount of time covered. And then finally, the last relationship we have here is going to be between velocity and acceleration. So if we remember back to physics or calculus, acceleration is just the derivative of velocity, right? So our acceleration, again a vector, is the derivative of velocity with respect to time. And that with respect to time is really important, right? The time relationship between all of these things is really, really important. When we integrate this acceleration with respect to time, we can get back to our velocity. Oops, sorry. So these are our relationships between position, velocity, and acceleration. There is one more relationship that we can derive, because it's not necessarily that we're always going to know the time, right? We may not know the time component, but what we can do is combine some of these equations in a way that we can get a relationship between position, time, and velocity in a way that, position, acceleration, and velocity in a way that doesn't include time. So we can see I have a dt in these two formulas here, and if I go ahead and solve these for dt, so if I have dt equals ds over v, and for my acceleration, if I have dt is dv over acceleration, and set those equal to each other, then I can get an equation where I don't actually need a time component in order to solve. If I set these equal to each other, I get ds over v is dv over a. If I rearrange this, acceleration times ds is going to be v dv. So now I have a relationship between those things where maybe I only know my acceleration as a function of position. Maybe I don't know what any of the time is whatsoever. But I can use this relationship, if given acceleration, position, and velocity, to find some missing component that I'm looking for. You know, given an acceleration and a position, I can find a velocity. So these relationships, just highlight these. I'll do that in yellow. Here we go. These relationships between position, velocity, acceleration, and time are what we're going to be using with our rectilinear kinematics and our kinematics in general. But this is the most generalized, most simple form for our kinematics, are these base relationships between position, velocity, acceleration. One other special case that we should look out for when we're working with these kinematic relationships is that there is a special case when we have a constant acceleration. So if we go ahead and look at those formulas that we just discussed, our acceleration is dv dt, our velocity is ds dt, and we had that last relationship where acceleration times ds is v dv. So in the event that acceleration is not dependent on time and it's not dependent on position, it's just a constant, what we can do is integrate these with respect to that constant acceleration, right? So we can say a dt, just rearranging this first equation that we're given here, this a dt, if we integrate that from 0 to t, and then we're left with our dv on this side, if we integrate dv from an initial velocity to a final velocity, what we're going to get is a, and then integral of t is just t. And then here we're going to get integral of dv is just v, which is v minus v naught. So v equals v naught plus at, just rearranging it. And sometimes you'll see it with like a subscript to it, ac for constant acceleration. So v equals v naught plus act. And this guy looks pretty familiar, right? This guy we've seen before, probably as early as our high school physics class, right? It's one of our kinematic equations that we saw a lot when working with things like projectile motion problems. So this is where this comes from, right? These kinematic equations that we've seen so much before aren't coming out of nowhere. They're coming from these integrals. They're coming from these derivations, these relationships between acceleration, position, and velocity. So we can show the same thing here with our v equals ds dt. If I rearrange this, so that v dt equals ds, and I take an integral so that I can get rid of those dt's. So I'll go from an initial time of 0 to a final time of t, and then from an initial position, s naught, to a final position of s. When I integrate this, I'm going to get, sorry, let me do this side first, s minus s naught. Erase this, because I skipped a step, and what I need to do is I need to substitute this v equation that I got over here into this integral. So I'm actually taking the integral from 0 to t of v naught plus act dt. Right? The reason that I have to do this substitution is because my v is in terms of t. My v is not constant. Acceleration is constant, but velocity is not constant. I have to do this substitution so that I can capture that t, I can capture that constant acceleration, and then do my integral. When I integrate this, I get v naught times t plus 1/2 a t squared equals s minus s naught. And this is another kinematic equation that we've seen before. I saw this guy all the time in physics. And then finally, we can go ahead and look at our last kinematic equation on the end here. So when we integrate each side, integral of a ds, and there we're going from our initial position to our final position, s naught to s, of our acceleration, again, constant acceleration, a sub c ds equals the integral from v naught to v dv. And notice I didn't actually have to do the substitution this time because I'm not integrating with respect to t, I'm integrating with respect to v. Right, so my equation is already in terms of v, this v dv, so I'm just going from my initial velocity to my final velocity. So when I integrate this, I'm going to get ac times s minus s naught is 1/2 v squared from v naught to v. I need to plug those in. I'm going to get ac times s minus s naught is 1/2 v squared minus v naught squared. Oh, and that's looking pretty close to another kinematic equation that we've seen before. I rearrange this just a little bit into a way that we've probably more commonly seen it. V squared is v naught squared plus 2a times s minus s naught. So it's good to bear in mind that if our acceleration is constant, we can use these kinematic equations to save us a little bit of steps in integration. Because for most of these kinematics problems, we're going to have to perform either derivation or integration to get whatever we're looking for, whether we're trying to find a velocity or a position or the acceleration or the time it takes to do something. Any combination of those things, we're probably going to have to do an integral or a derivation, unless we have this constant acceleration. And then in that case, we can just skip ahead and use these kinematic equations, use these constant acceleration equations just to save us a little bit of time. But let's go ahead and take a look at some examples of how we can use these. In our first example here, we have a car moving in a straight line such that for a short time the velocity is defined by v equals 3t squared plus 2t. Determine its position and acceleration when t is 3 seconds, given that when t is 0, s is 0. So the way that I like to approach any kind of problem in dynamics is I really like to list out everything that I'm given and what I'm trying to find so that I can really find those equations that I need that build those relationships between the two. So this one is fairly straightforward in what we're given. So if I write down everything that we're given here, we have, I think I'll do this in white, move that. Whoops. All right, so we're given a velocity function. Velocity is 3t squared plus 2t, and that's in feet per second. Already we have this relationship between velocity and time. We're also given that at the initial time t is 0, that our initial position s is also 0. What we're trying to find is we want to determine its position and acceleration when t is 3 seconds. So we're trying to find what s is at t equals 3 and find what acceleration is at t equals 3. So you remember we have relationships that get us between velocity, position, and acceleration all with respect to time. So let's go ahead and write those out. Write out some of those equations that we've been looking at. So we have velocity is ds dt, is the derivative of position with respect to time. So we know that if we integrate our ds, forgot my dt over here, v dt, so just rearranging this equation, v dt equals ds. That I can integrate this with respect to time and with respect to s to get a position function. Right? So if I integrate from an initial time to my final time, I can either do this to time t, or I can go ahead and do it to the time that I'm wanting to do it at, that t equals 3. And I want to find that position. So I'm going from my initial position, which the prompt gave us, initial position was 0. That'll be my lower bound on the integral here. And then I want to go to my position s. This is what we're looking for. We don't know what s is. This is what we're trying to find. So when I perform this integral, on my right side here, I have ds integrated from 0 to s is just going to give me s. Hold on just a little bit. It's just going to give me s. And when I integrate my v with respect to t, well, bear in mind that my v is in terms of t. We're given this function up here, where v is in terms of t. So this integral is actually going to be from 0 to t of that v function, 3t squared plus 2t dt. So if I integrate this with respect to t, I'm going to get 3t squared. If I integrate that, that's going to give me t cubed over 3, and then the 3's cancel out. Plus 2t, when I integrate that, that gives me t squared over 2. The 2's cancel out. T cubed plus t squared from 0 to t. This is actually what it gives me. T cubed plus t squared. And now I could have, again, set my bound at 3 since I wanted to know position at 3, or I could just plug it in now. So I get my position is going to be 3 cubed plus 3 squared. Means my position at 3 seconds, when I plug that into the calculator, is 36, and pay attention to units. Note that our units were given to us in feet per second, which tells us that our position is going to be in feet. That's an F and a T. I know that looks like an H, but that's not what I'm going for. This is feet, FT. That looks a little bit better. All right, so simple as that. Just taking that relationship between position and velocity, performing an integral gives us position. And we have a very similar type of relationship with acceleration, right? We know that acceleration is the derivative of velocity with respect to time. So this almost feels probably a little bit easier to us, right? A derivative is usually a little bit easier to take than an integral. So all we're doing is deriving, we're taking the derivative of that velocity function that we were given with respect to time. So derivative with respect to time of the v function. 3t squared plus 2t. So the derivative of that is going to be, if we bring the 2 down, that's going to be 6t plus 2. And then again, we want to know that acceleration at 3 seconds. So it's just as easy as plugging in 3 for our time, punching that into our calculator, and finding our acceleration of 20. And then again, units were in feet per second for velocity. So that's going to be feet per second squared for acceleration. And you can see all of these values are positive based on the little car diagram that we were given here at the beginning. Everything is moving to the right. We can just assume that to the right is positive. All of these values are going to be positive. It's just a matter of manipulating those relationships with the equations that we know, manipulating those relationships to find whatever piece of information we're missing. But let's take a look at another example. In this problem, we have a test rocket traveling upwards at 75 meters per second, but when it's 40 meters from the ground, its engine fails. So we want to determine the maximum height reached by the rocket and its speed just before it hits the ground. While in motion, the rocket is subjected to a constant downward acceleration due to gravity of 9.81 meters per second squared, and we're going to neglect air resistance. So a lot of these dynamics problems have a lot of information at the beginning to take in, but we really want to break it down and really picture what's going on. Not every dynamics problem will give you an image to work with, but they do paint a picture with words a lot of times. So we have a rough diagram on the left there of kind of what is going on. So what happens in this is that the test rocket takes off, it has propulsion, but then the engine fails. So at this 40 meters, our engine goes kaput, and the only thing driving it forward was the acceleration that it had, but now it has no more acceleration pushing it upward. Nothing else to push it upward. It only has gravity on it, acting on it, bringing it back down to Earth. So it has this initial velocity in this condition. This initial velocity says it's 75 meters per second. So that's our initial velocity here at, we'll call this point A. So here at A, our velocity at A is 75 meters per second. And then we know it's not just going to be 75 meters per second going up into the atmosphere, continuing on to eternity, right? Because it has gravity acting on it. It's still on our Earth. It only made it 40 meters up. So it's going to come back down because of that downward acceleration due to gravity. But notice, this is actually giving us a special case, right? There's no other forces, there's no other accelerations acting on it. The only thing that's happening to it after its engine fails is this constant acceleration, which means, lucky us, we get to use our constant acceleration kinematic equations. So hopefully that'll make solving things a little bit easier. So speaking of, what are these things that we're solving for? So we're given the 40 meters start, the initial velocity of 75 meters per second. We want to find, just as a reminder, we can pick it out of here, the maximum height reached by the rocket. So we want to know what the height is right here. And we'll call that, let's call this position B, and then maybe when it hits the ground, we'll call that C, just so we know what points we're talking about here. And so we want to know this distance, right? The maximum height. Call this the position of B, right? If this is our origin, we could also, instead of calling it C, we could call the ground the origin. Right, so from the origin, it fails at 40 meters up. We want to know its maximum height. What is this position at B representing its maximum height of this flight? So we want to find SB. And its speed just before it hits the ground. So we want to know, as it's coming down on this down return here, right, what is the velocity here at point C? What is that velocity right as it's hitting the ground? So now we know what we're looking for. We can see some of the things that we're given, and we can recognize a few other things that aren't necessarily explicitly stated. Right, so one thing that we might observe that we can assume, it's not explicitly stated in the problem, is that since what comes up must go down, at this inflection point, at this turnaround point, where we're changing from a velocity being positive to a velocity being negative, we're going to have a velocity of 0. Right? The velocity at B we know is 0 meters per second. Because of that deceleration acting downward on it, that velocity has to go from a positive to a negative due to the negative acceleration. And let's write down our handy dandy. We know this is a special constant acceleration case, so we can write down all of those kinematic equations that we had. So the first one we had was V is V naught plus ACT. Second one we had is S equals S naught plus V naught T plus 1/2 ACT squared. Notice I always say these little zeros at the bottom on these as knots, those little initial positions, as knots, which is just another term for 0. This is the most common way I feel like I hear it. Some people say V0, some people say V naught. I always say V naught. That's just how I was taught, just a habit. But that's all it is. It just means 0. We have v squared is v naught squared plus 2ac s minus s naught. So those are all of our special condition, constant acceleration, kinematic equations. So now for these two things that we need to find, is there kinematic equation of the three that gives us, that includes all of the things that we know and doesn't include one of the things that we want to know? Let's say for SB, we'll start with SB. So we know our position at A, we know our velocity at A, that can act as an initial velocity. We know our acceleration. We do not know a time. So we have two positions. We have one unknown position that we want to find. We know an initial position. We know an initial velocity. We know a final velocity. We know an acceleration. We don't know any time. So we do not want to be using any of these guys that have time in them. Really, these first two that I wrote were just a waste of my time to write them, right? I don't actually need to solve for time in any of these. Now you can, if you wanted to, you could use, you know, equation 1, plug it into equation 2, and you could solve for a time, and then you could use that time to plug into another kinematic. But I don't actually need to use 1 or 2 at all for these problems. To solve for both SB and VC, both of them I can solve just using number 3. Just using v squared equals v naught squared plus 2ac times s minus s naught. So let's look at our, not v, let's look at SB first. Solving for SB first. My final velocity, so my velocity at B is 0. I have 0 squared equals my initial velocity at A was given as 75 meters per second squared plus 2 times constant acceleration. Now remember, this acceleration is pointing downwards, and so for this system I'm going to assume that up is positive. So since my acceleration is pointing downwards, I need to have a negative sign on here. It has to be negative 9.81 for that acceleration. And then multiply that by the change in distance. So I know my initial position is 40, but I don't know what that final position, what that SB is. That's what I'm trying to solve for in this. So I can plug this into the calculator, rearrange it a little bit to solve for SB, right? SB is the only unknown in this equation. If I plug it into a calculator, I'm going to get SB is about 327 meters. Give or take, I rounded a little bit. SB is 327 meters. And now that we know that, we can use this exact same equation that we had to solve for VC, where now our initial condition is B and the final condition is C. So exact same thing for VC. Let's use a different color actually. Do this one, blue. So for our VC, we're going to have our final condition, VC squared. And now that initial velocity is 0, right? Our initial condition is B, our final condition is C in this case. So 0 squared plus 2. Again, remember that it's negative 9.81 times our final position, which we know is the ground, 0, minus our initial condition, which we just found. We just found that SB is 327. So when we punch that into a calculator, we can get our velocity going, our velocity there at C, our velocity as we hit the ground, going to be negative 80.1 meters per second. Now that of course is velocity, it's a negative sign because it's going downwards towards the Earth, but the question did just ask for speed, so I really don't need to say negative 80.1 meters per second. I can just say speed is 80.1 meters per second. Speed does not get a negative sign on it, it's just the absolute value of your velocity. The speed is 80.1 meters per second. Just recognize the difference there between that speed and velocity. Velocity has to have the negative sign. Let's take a look at another example. Here we have a particle traveling along a straight line with an acceleration of a equals 10 minus 0.2 times s. We want to determine the velocity of the particle when s is 10 meters if v is 9 meters per second at s equals 0. Again, a lot of these can sound like a lot of words. So it's really important to draw something. If there's no image given, it can be really, really helpful to draw a picture, or at the very least, pick out those pieces of information that are actually going to help you solve something. So in this case, we have some particle, it's traveling along a straight line, and we're given this acceleration relationship. Okay, so here's my particle. It has an acceleration that is in terms of position. So whatever that position is matters. Given acceleration is 10 minus 0.2 times s, and that's in meters per second. Oh, meters per second squared, sorry. Meters per second squared is our acceleration. And we want to find the velocity, so find v when s equals 10. We're also given an initial condition here that says velocity is 9 meters per second when s is 0. And all of those s's are all position s's, right? These seconds for time, I'm going to leave those as seconds. And these s's are all positions. They're all distances. So you'll notice that we're not actually given any times here. Normally our go-between from position, velocity, acceleration is some kind of derivative with respect to time. But in this case, we don't have any relationship to time. We only have relationships between each other. Specifically, we have one between acceleration and position. Luckily, we have an equation that relates those things together. So this is where our handy-dandy A ds equals v dv comes in handy. Since there's no indication of time going on within this problem statement, we'll leave it out of it entirely, and we'll just use this relationship we have between acceleration, position, and velocity. And what we can do is go ahead and set up these integrals. So when I integrate, I want to integrate a ds and my initial position to my end position. So I know my initial position. I was given an initial position of s equals 0. So my lower bound is going to be 0. And then my end position I also know, right? I know I'm looking for when the position is 10. So I can go ahead and put that into my upper bound for this. Equals v dv. v dv. Now my bounds for my velocity, my lower bound is going to match the same bound as my position. So when s equals 0, the lower bound for my velocity is 9 meters per second. And then my upper bound will also match my upper bound for what we're trying to find here. So my upper bound was 10 meters for position, and my upper bound is unknown. This is the thing we're trying to find. So I'll leave the upper bound as just v for when we do this integral. Now remember, the equation they gave us for a is in terms of s, which means I'm going to have to plug this in for a before I do this integral, because a and s are dependent. They are related to each other. So when I plug that in, I actually get the integral from 0 to 10 of 10 minus 0.2s ds integral from 9 to v of v dv. So now it's just a matter of chugging through it to find what that velocity is. All of the setup is done, just a matter of basic calculations now. So when I integrate the left side, I'm going to get 10 times s minus 0.2 s squared over 2, evaluated from 0 to 10, equals, my integral of v dv is just going to be v squared over 2, and that's evaluated from 9 to v. So now I just plug in those upper and lower bounds. 10 times 10 minus 0. Well, I can simplify this to 0.1 from 0.2 over 2. 0.1 10 squared minus, and then I plug in my zeros, but that makes everything 0 here. And I can do the right side of my equation, v squared over 2 minus 9 squared over 2. So from here, with a little bit of rearranging, let's see, I think this side I get, 100 minus 10? And then that I can multiply by 2 to get the 2 off of that side, is v squared minus 81. If I simplify that, I get v squared equals 261. Take the square root, I get my velocity is 16.2 meters per second. Double check those units, does that match? My acceleration was in meters per second squared, so my velocity should be in meters per second. So that is my velocity at the position of s equals 10. Velocity is 16.2 meters per second. I didn't need to use time at all, only the relationship between position, acceleration, and velocity. Let's take a look at one last example together. So here we have Spider-Man moving along a vertical path with a velocity of 3t squared. Sorry, this is squared. It came through a little weird. 3t squared minus 16 meters per second, where t is time in seconds. He's initially located at the origin. Determine the distance traveled in 3.5 seconds, as well as his average velocity and average speed during this time interval. We're going to neglect air resistance. So for this example, for this last one, what I'd like you to do is go ahead and pause the video and see if you can figure it out on your own. Really try, make an attempt, see if you can get at the very least the distance traveled on this problem, and then unpause and we'll work through it together. All right, so let's talk about what's happening in this problem. Here we have Spider-Man on our vertical path. So Spider-Man, he's moving up and down. Our Spider-Man, and he's moving vertically along a path that is given by v equals 3t squared minus 6t. He's located at the origin. Determine the distance traveled in 3.5 seconds. So we want to find distance traveled, that's our s sub t, as well as average velocity and average speed during this time. So one thing that we may or may not notice when we go into this problem is that this velocity equation that they've given us is a quadratic function. So one of the things that we may want to do when we're given these equations, when we're given these relationships, and we're trying to find the total distance traveled, is go ahead and plot that velocity function. See what that graph looks like. Because if I plug in this velocity function into a calculator, Desmos, some graphing software, I'm going to find that my graph is actually going to look like this. Where here, at t equals 2 seconds, I'm crossing this threshold of 0. And when I get to t is 3.5, I have a positive velocity. Right, so my velocity represented by this quadratic function, my velocity actually starts out negative, crosses through 0, and then becomes positive. So what does that mean? What does it mean for what's actually happening as Spider-Man is traveling? Our velocity, he has a negative velocity, so he is traveling downward, as I've assumed him to be, slinging from his web up here or whatever. That looked more like a web. There's a Spider-Man's web. Swinging from his web, he swings down, comes down until his velocity hits 0, and then velocity becomes positive. So he comes back up, slinging down and up on his web. And we can see that if we go and look at, you know, a clip from the Spider-Man movie. There's Spider-Man. We can see Spider-Man goes down. His velocity equation of representation. He's grabbing Mary Jane. He comes back up with her. That's the actual path traveled by Spider-Man in this problem. Right? So he comes down, catches Mary Jane, comes back up. So what's really, really important to note there is if you don't recognize that this is a quadratic formula, that this is a parabola, that you're going down and coming back up, then what you might have done is integrated, right? Because we were looking for our position. We're looking for that distance traveled. You may have integrated this velocity equation with respect to time. 3t squared minus 6t dt going to give us our position. So when we integrate this over the time interval from 0 to 3.5 seconds, I get t cubed minus integral of 6t is going to be 3t, sorry, just 6t, oh yeah, integral, 3t squared from 0 to 3.5 gives me my position. And so if I plug in that 3.5 number, what I'm going to get is, I think it's 6.125 is what I get in my calculator when I plug in 3.5 into this position formula. But again, this is just position. It just tells us that at the end of the clip, he's 6.125 meters higher than where he started, but it's not the total distance traveled. The total distance traveled has to account for the fact that he came all the way down in that 2-second interval and came up, right? So v is 0 at the bottom here. It took him 2 seconds to travel downwards, and then he travels back up. So we have to account for that time. We have to account for that time that he's gone through in essentially two separate calculations, two separate intervals there. If I look at this integral that we just did for our position, we can find the position at 2 seconds. Right? If I plug in t equals 2 instead and make my integral from 0 to 2 for 3t squared minus 6t to get the position, I can get that my position is 3t, again, same formula, 3t minus, or sorry, t cubed minus 3t squared. Plugging in 2 gives me a position of -4. Right, so we have to account for the fact that he goes downwards by 4 meters, comes back up by 4 meters, and then ends up in his ending position 6.125 meters. So all of those distances added together are what are going to give us the total distance, that ST of 4 plus 4 plus 6.125 gives us the total distance that Spider-Man traveled. Total distance traveled of 14.125 meters. And I know that was kind of a mean one. It was kind of a tricky problem. We hadn't done one with this distance traveled where it matters that you're really changing directions, and you're going to have to be taking that into account and really being cognizant of that. Before we move on, I think we had a couple of other things to solve here. We got the distance traveled, but we also need his average velocity and average speed, which also may have been a tip off to you that, hey, average velocity and average speed may not be the same number, because velocity accounts for the sign. Velocity is a vector, it has direction, whereas the speed does not. If you recall, our average velocity equation is the change in position over the change in time. So that's our final position minus our initial position, and we started at 0. So our change in position is going to be the 6.125 over the total time, 3.5 seconds, to get an average velocity of 1.75 meters per second. Whereas if we calculate speed, speed accounts for all distance traveled. It's the total distance traveled over that same time interval. So we found our total distance traveled to be 14.125. Total time is still the same, 3.5 seconds. Plug that into a calculator, get about 4 meters per second for the speed. Again, velocity has direction, that speed is going upwards because he does end up higher than where he started, but speed does not. Speed does not have direction. It's only that averaging of the total movement, right? Again, this one was meant to trip you up a little bit. It was meant to be a little bit difficult. It was really to show that sometimes graphically, it can be really, really beneficial to plot what's happening. You're given some kind of equation, it can be really beneficial to have that visual aid, a graph of what is going on. And so that's what we're going to look at in our next video. We're going to look at erratic motion and how this is represented graphically.